Hello everyone. Welcome to my lecture on multivariate random variables again. Uh, we have already covered several topics in this chapter. I'm actually following this Demidengo's textbook, and we are now in chapter 3. Uh, So we have already covered topics joint and marginal CDF, joint and marginal PMF, joint and marginal PDF. We have looked at the definitions and some examples of those. And then we looked at connection to Dirichlet's distribution and then expected value. And then we looked at uh, the common definition of independence of two random variables. Uh, Under that, we discussed expectation of the product of two independent random variable and also the variance of the sum of two independent random variables. And then we looked at several examples combining all those topics. And then we started a new topic in the last lecture on conditional distribution. In that lecture, we discussed the definition, conditional probability mass function, conditional probability density function. And after that, I explained an example. We looked at an example where, on how to generate some bivariate data from a given joint probability density function, right? How to generate data from a bivariate distribution, a given distribution, when the density function is given. So we looked at one example where we looked at how to generate the data from a uniform distribution defined on a triangle, right? So the general method that we applied was first generate uh, a random number x according to the marginal distribution of x. And then secondly, generate a y value from the conditional distribution of y given the previous value of x. So thereby jointly x and y uh, has the expected joint density function. So that is the general method that I followed. And we completely discussed this example. Uh, so today, to continue from there, I will look at another example of generating data from a multi-variate. In this case, I'm considering again a bivariate distribution. And then we will go on to new topics. I will look at another definition or another way to define the independence of two random variables. And then we will look at some formula, we can call it Bayes formula. We already know Bayes formula regarding the probabilities. Here we are going to look at the Bayes formula corresponding to random variables. And then we will look at conditional mean and conditional variance. Uh, so there will be several examples on those. Right. And today's lecture will again be consisting of three parts. Each part will roughly be of length 1 hour. So altogether, roughly 3 hours. Right. So I will now move on to the new example on how to generate data from a bivariate distribution. Right. So this example comes from again Demidengo's book. This is example 3.34 in the book. So what we are planning here is to generate data from this particular joint density function. Actually, in this joint density function, the domain or the support contains x and y both. That is, this we are looking at a certain subset uh, in the real plane. But of course, the density function here involves only x, right? So what we want to suppose we want to generate data from this particular joint density function. So how do we do that? So first of all, as I mentioned, the method that we are going to use is generate x value from the marginal distribution of x, and then generate a y value from the conditional distribution of y given that value of x. So thereby jointly x and y will have the required distribution. Right. So therefore we need first of all to find out the marginal distribution from this joint density function. Marginal density function of x is required, and also the conditional distribution of y given x is also required. So we will first find out those two. So as I have already mentioned, it's good actually to draw the support of the joint density function always to get an idea, especially when we want to integrate the joint density function to get the marginal density function and also the conditional distribution in order to find out the conditional distribution using that and so on. It's always useful to look at the support of the joint density function. Here I have drawn the support of this joint density function. Here notice that uh, uh, y is greater than or equal to 0, y is less than or equal to x is less than infinity, therefore y is also less than infinity. Of course, we are looking at an exponential distribution here with rate 1. Right. So here, actually, this is not exactly the support. The support goes up to infinity in the x-axis and goes up to infinity in the y-axis, but restricted by this y is equal to x line. We are considering y less than or equal to x region. That is our support, right? Even though it looks like it is ending at 6 here, it's not like that because we cannot draw the graph until infinity. I have selected a certain region, but remember, so therefore it's going up to infinity. So this is the joint density function given by this expression here, right? So here, this is the 0, 0 point corresponding to this point here. And then you can see that it has the exponential shape, right? It's decreasing and going up to infinity, of course. And now in this case, of course, we are looking at a surface. So the surface is like this, right? So first we want to find out the marginal distribution of x, right? So in order to find out the marginal distribution of x, of course, you have to integrate the joint density with respect to y, with respect to y, right? So therefore, we will first consider some vertical line here at some value of x, and then we will have to integrate the joint density function along that line uh, with respect to y, right? So let us, for example, consider mm, a vertical line, for example, at some x value. Okay, whenever I draw this, it has to be a vertical line. So suppose this is some value x here, right? So we have to integrate this joint density function along this line with respect to y. So y goes from 0 up to here. So in this case, y is equal to x. So therefore, we have to integrate the joint density function from 0 to x with respect to y to get the marginal density function. Okay, so the marginal density function of x is given by this integration of the joint density with respect to y from 0 to x, and this is what we get. So this is x times e to the power minus x for x greater than or equal to 0, right? So this is for a given x, right? It has some kind of shape of an exponential distribution, of course, but when you consider it as a function of x, it's not an exponential distribution. Exponential distribution has the form, for example, lambda e to the power minus lambda times x, right? So it's not an exponential distribution, but this is you can identify by comparing with a gamma distribution, right? A gamma distribution has this particular formed density function. I'll write down the density function for you to compare. Um, right. So for the gamma density function, fx is equal to e to the power minus x lambda, x to the power alpha minus 1, and then divided by gamma alpha, and there is also a lambda alpha. Right. So you can see that this has this form because there is a x to some power here. So this is that term. And then e to the power something times x. So this one, right? Lambda is a constant and alpha is a constant. So in this case, you can see that x to the power 1 here. Therefore, alpha minus 1 has to be 1. So alpha is equal to 2. And here e to the power minus x times lambda, where lambda here is 1. So therefore, we can then, of course, when you say alpha is equal to 2, gamma 2 is equal to 1. Gamma 2 is the same as factorial 1, right? If, for example, the number here, if you consider gamma n, for example, if n is an integer, we know that is equal to n minus 1 factorial. So using that, gamma 2 is equal to factorial 1, which is 1. And when lambda is equal to 1, of course, this is 1. So therefore, you can see this is actually the density function of a gamma 2-1 distribution, right? So it's not an exponential distribution, it's a gamma distribution. Right. So now we want the conditional distribution of y given x. So conditional distribution of y given x by definition is equal to the joint density function divided by the marginal density function. So we know the joint density function already. Therefore, we have just found out the marginal density function. Therefore, when you simplify, this is the conditional distribution of y given x. So notice that this is a function of x because this is the conditional distribution of y given x. Right. So in this case, y has to be between 0 and x has to be greater than 0. Of course, both have to be less than infinity. Right. So therefore, I can write down more formally, more correctly as the conditional distribution. It's equal to 1 over x if y is in this range. This simple x is this x appearing here. Otherwise, the conditional density is equal to 0. Uh, look at this function now. Actually, now this thing is 1 over x for y between 0 and x, right? So for a given x, of course, this is a constant, right? So this is the conditional distribution of y given x. You can see that for a given x, this is a constant and y changes from 0 to x. So it's almost like this. For example, the usual uniform distribution, if you remember, right? So for example, suppose some random variable, say z, has a uniform, say from 0 to some value a, then f z will be equal to 1 over a, where z is between a and 0. So what you have is a very similar thing here, right? 1 over x where x is a given value now, it's not a random variable, and we are looking at this function evaluated at y, and that y is between 0 and this x here. So it's exactly like this. So we can identify by that this is actually the uniform distribution. The density function of a uniform distribution when the domain or the support actually is between 0 and x. Right. So we have identified. It's okay to not to know the name actually, but in this case we know the name of the distribution in both marginal and the conditional. But of course, we don't need to know the name. Uh, it's enough to have the formula in general. Right. So y given x has a uniform distribution in 0, x. So now what we do is to generate pairs of observations, xi, yi, right? If you want to get several, what we do is first of all generate an xi from this gamma to 1 distribution. And then with that simple xi, generate yi, which is a uniform random number from 0 to x. So we know this x. So therefore we can generate a number from a uniform 0 to x distribution. So then those pairs of observations will have the required joint density function, right? So here I have written down some R code. Of course, I have chosen a smaller font because I wanted to include everything in this one slide. So these are the things. N is a given number here. This is the number of observations I require, number of pairs of observations. So what I have done here is I first of all generate uh, n numbers from gamma distribution. Those are the numbers that I will be using as x1, x2, x3, and so on, observed x values. So they are coming from a gamma distribution with shape 2 and rate 1. So I have, for example, if n is 10,000, then I'll have 10,000 gamma observations here. And then I need for each of those x values, I need one for a given x, I need one random number from uniform 0 from 0 to that x. And then for the next x also, I need one observation from uniform 0 to that x and so on. So I can get now x is a vector here. So if I say y is equal to r unif and then number of observations is n and minimum value is 0 and the maximum value is not a single number in this case, a vector of these n x values. So in that case, what this will do is will generate uh, one observation from each uniform from 0 to particular xi. So thereby I'll have n y values. So that will give me the pairs of observations. So I combine them as a data frame x and y, right? And we can get that out of this function. I call it R bivariate exp, right? So that is, those are the commands, so the codes that is required. So I generated about, I think, 10,000 numbers using this. And I just have drawn the scatter plot, just y versus x's, just to see how those observations are appearing in a scatter plot, right? So this is what I get after generating 10,000 numbers. So you can see that actually all the numbers are in this particular subset. So this is actually the correct way, more correct way to show this support here. I should not have stopped here, right? I should have looked at all these things. So this graph is much more clearer. So it's saying that it's going up to infinity and up to infinity here. But anyway, you can see that most of the observations are clustered where, around this cone, and then only very rarely observations are appearing here, right? So if you compare this, now this is the set of possible values. Of course, if you look at the density, density is very high here and density is very low here. So that you can see is very, very well matching with this theoretical joint density function, right? So close to 0, 0, the density is very high, and then it gradually decreases the density. So we can clearly see the same effect here, right? The density is very, very low as x is increased, and then density is high here, right? It's all the values are between. So this is the y equal to x line, right? And then you can see that the support here, this graph is the same as the support in the joint density that I showed earlier. So that is the way that is one way that we can use to generate data from a bivariate distribution with a given joint density. Right. So first generate the data from the marginal distribution of x, and then generate the data from the conditional distribution of y given x. Of course, you can do the other way also. You can first generate the an observation from the marginal density function of y, and then generate the data from the conditional distribution of x given that y. That is also possible, right? So whatever the way that mathematically convenient you can use, because of course you have to find out the marginal density function of one variable, and then you have to find out the conditional distribution of the other variable given the first variable, right? Okay, so that was kind of a continuation for the previous lecture. I had only looked at only one example of generating data, so that now completes with two examples. Uh, Now we will look at another definition or another way to define the independence of two random variables. When I say another, that means we have already looked at one definition. That is, uh, we say x and y are independent if and only if the joint density, right? So let me remind the previous definition. We say x and y are independent if and only if the joint density function x, y can be written as the product of the marginals, right? For all x, y such that fx, y is greater than 0, right? And you can define the independence of two discrete random variables also in the equivalent form using the probability mass function. This is for the two continuous random variables, right? So in general, actually, we don't have to exactly show that this is equal to that, as long as if we can show that fxy joint density function is proportional to the product of these two, right? Then the proportionality constant has to be the normalizing constant, of course. So what you really need to show in order to show that two random variables are independent in the continuous case is that the joint density can be factored, right? So it is equal to something times f of x times fyy, right? If you can show that it can be factored like that, that is enough, right? And for the discrete case, of course, you can write down using the mass function, the same thing. That is joint probability mass function is equal to the product of individual mass functions. Now we can define the independence of two random variables using the conditional distribution. Right. So again, let me remind, we actually when you talk about events, right? Excuse me. When you want to talk about the independence of events, say X and Y, right? Generally, we defined events A and B are independent if the conditional distribution, right? If the probability that X, in this case, two events, probability of A given B is the same as probability of A, or equivalently, if the probability of B given A is the same as probability of B, then we define A and B to be two independent events, right? And going with the same idea, we can define now uh, the random variables x and y are independent if and only if the conditional density equals the marginal density, right? So that means uh, if the conditional distribution of one random variable given the other one is equal to the marginal distribution of the first variable here, right? So that you can see it's very similar to the idea in the events, right? Independence of events, right? So we can actually prove this thing using the previous definition of independence, right? So let's look at suppose that x and y are independent, right? And then, according to the previous definition of the independence, we should be able to write down the joint density function. I have missed here the usual capital XY subscript, but it is, I think, understood, right? So here, generally, I write down XY here. So the joint density function of X and Y evaluated at simple XY is equal to the product of the marginals if X and Y are independent. So therefore, if we now look at the conditional distribution of Y given X, it is generally equal to we know that's equal to it's equal to the joint density divided by the marginal density of X, but now joint density is equal to the product, and therefore we can write down that as this, and then this cancels out, and therefore uh, we have this conditional distribution of Y given X is equal to the marginal distribution of Y if X and Y are independent. We can show it the other way around also very easily, right? So this is an if and only if condition. So here we have shown it on one direction. We can easily show it in the other direction also. Now, if this condition is satisfied, then uh, we can look at the that thing by expanding using the definition, and then you will see that this joint density function is equal to the product of the marginals, right? So if this happens, then this condition happens, which is again the definition of the independence, right? So therefore, it's very clear, right? Now, using this idea, right, of independence, either the first definition or the second definition here, we will now look at an example uh, where this idea of independence will be used. Right? Suppose x and y are independent continuous random variables, and suppose we are interested in the joint density function of x and x plus y. Of course, now you should be able to see that even though x and y are independent, x and x plus y are not independent because the second term also contains x, right? So statistically also they will not be independent in general, right? So what we need is the joint density function of these two new random variables. Of course, one is the same as the previous one, but the second one is a new one. In terms of the marginal densities, right? So first of all, we'll see whether we can define, right? We can write down the marginal densities, but we will try to get the joint density function, right? The importance of getting it in terms of marginal densities is that because we are assuming that we know the marginals of x and y, so if we can get a formula to find out the joint density in terms of marginals, that will be more convenient. So yeah, that's the importance of this particular example. Try to get uh, the joint density of these two random variables in terms of the marginals of x and y. Right. So therefore, because now we are considering a new situation, let's give them two new names. Let's say consider u is equal to x and v is equal to x plus y. So what we are interested in is the joint density function of u and v. Right. Uh, there are several methods to derive this, but in this case, up to now, we have not discussed more than one method. The method that we have discussed is first to derive the uh, joint cumulative distribution function and then take the derivative of that to get the density function, joint density function. So we will use that for the moment. And once we discuss the other method, we can use that method. So that's called method of transformations, right? So we will use this method for the moment. So we are looking at the cumulative, joint cumulative distribution function of u and v. So by definition, that is equal to the probability that u is less than or equal to simple u, and v, capital V, is less than or equal to simple v, right? So when you write down them u and v in terms of x and y that we already know, we get this expression. And now notice that this one, x less than or equal to simple u and x plus y less than or equal to simple v. Of course, this one I can write down like this one is still the same, but I can write down this one as y less than or equal to simple v minus x. Right. So now we know already how to find out probabilities like this, joint probabilities, right, in terms of x and y. What we have to do is we have to integrate the joint density function over a subset of the support of the joint density function satisfying this particular condition, right? So what we are looking at is a set of u and v values satisfying. Actually, we have to integrate the joint density with respect to x and y. So what we are looking at is x and y subset, right? X y subset of the support of the joint density of x and y. That's what we are looking at. So that subset should satisfy the set of x values should be less than or equal to u, and y values should be equal to less than or equal to v minus whatever the x that we are considering. Right. So as I have already mentioned, it will be better, easier if you look at the support of this joint density function of x and y first. Now notice here we are saying that x and y are independent. Therefore, the joint density function will be actually equal to the product of individual densities, but we will use that fact a little later. We will first consider the joint density function, right? So I have not drawn that one, but we can easily see that what we are looking at here is a certain subset, so that x less than or equal to some value u, and then y less than or equal to v minus that uh, simple x value that we are considering. So therefore, the integration should be like this from generally, right? In general, because we are not considering a particular density function here. So theoretically, therefore, we have to integrate from negative infinity, right? If you're considering the derivative with respect to y first, it's not the derivative, integration. Integration with respect to y first, it's going to be from minus infinity to v minus x, right, for a given fixed value of x, right? So v minus x, and that x then has to change from minus infinity to u because x has to be less than u, right? So that's why this expression, the probability, is given by this expression here. Joint density has to be integrated. I'm usually integrating with respect to y because in that case I can consider a vertical line on which I am integrating with respect to y. In that case, x will be changing from minus infinity to v minus x. So we have to consider a subset here separated by x equal to u line and y equal to v minus x line, right? So then uh, when you're changing for a given x, y will be changing from v to simple x, right? So that's why this integration, and that u has to be from x has to be from minus infinity to u, right? I suggest you to draw this in the two-dimensional plane, then it will be this will be very clear, right? But because x and y are independent, we can write down the joint density as this, and therefore the previous expression now here I can replace with the product of marginals. Now we can see that this is a function of x only, this is a function of y only. So when you are integrating with respect to y, first you can take this fx out of this integration and then consider this one. And then, of course, dx will come after that, right? But if you look at this one, this is by definition, this is the cumulative distribution function of capital Y evaluated at this value here. We are integrating the marginal density from minus infinity to some value. So therefore, that will give you the cumulative distribution function of Y evaluated at this value here, right? So now we have this expression in general, right? If x and y are independent for the cumulative distribution function of u and v. Right? But what we are really interested in is actually the joint density function of u and v. So we have to differentiate this thing with respect to u and v, simple u and simple v. So that for that we have to use a mathematical theorem called fundamental theorem of calculus, right? So that is one method, right? So after this thing, we will look at, right? So I'm going to give you another way of coming to the same position here, starting with uh, using the conditional distribution. Here we are just looking at this one. So, but somebody might look at the conditional distribution, but it's not necessary, but I'm just showing that you can do that also, right? So this is where we were here at this point. This is the same as that. So we can come to that. So that is after that, the next one also. But now if somebody wants, you can write down this one in terms of the conditional distribution, right? Conditional distribution of y given x times fxx, right? So that is generally the correct formula, right? For because we know that the conditional distribution is equal to this thing divided by this. So therefore, this one we can write down as the product of these two, right? Now, the same idea, of course, we have to integrate integration, limits of integration are going to be the same as previously, right? When you are integrating with respect to y, it goes from minus infinity to v minus x. Integrating with respect to x will go from minus infinity to u, right? So now you can separate this thing out when you are differentiating with respect to y, and then consider with the fxx after that. Because here we are integrating this function with respect to y for a given x, for a fixed x. So in this case, as far as this integration is concerned, x is fixed. The variable, mathematical variable is y. So therefore, we can separate that out and do it and then multiply and then do the whole integration after that. But notice here, this is the important that I wanted to show you, that you can write down this thing as a condition in terms of conditional probabilities also. Right? So what I really wanted to show you was that this joint probability can be written as an integration of the conditional probability times the density function. So this expression, this one is equal to this thing, is commonly used in a lot of places. And if somebody wants to understand how that comes, that's what I wanted to show here, right? So you can see that this is actually the probability that the conditional probability that y less than or equal to v minus x given x is equal to simple x. In other words, this is actually the conditional CDF. This is the conditional CDF of y at v minus x given x is equal to x, right? So that is another way to write down. But here I have written down it as a probability, and then you have this, right? So, but notice here the conditional probability regarding y given x is the same as the unconditional probability regarding y because x and y are independent. So that is where the independence is used here, right? So this conditional probability is the same as the unconditional probability y less than or equal to v minus x. And then you have this density function, right? So therefore, I have this expression. And now again, as previously, if you this, I can write, I have written down as the uh, that conditional cumulative distribution function becomes the marginal cumulative distribution function because x and y are independent. So this is the marginal cumulative distribution function of y evaluated at v minus x times the marginal density function of x, which is the same as the expression that we had here, right? So the purpose of showing these steps was actually I wanted to show that a commonly used expression, a probability regarding x and y like this can be written as an integration of the probability, conditional probability times the density. And that is very similar to what we discussed in when you're talking about events, the law of total probability, right? Rule of total probability. It's very similar to that idea, right? Okay. So anyway, now what we want is to get the joint density function of u and v. So in order to obtain the joint density function, I have to use this uh, fundamental theorem of calculus because I am going to differentiate an integration. Right? I have to do it twice. So just to remind you that what this fundamental theorem of calculus is, suppose that you have some function like this. You are integrating some function gx with respect to x, but put in the limits from minus infinity to u. Then finally, this will become a function of u, and let's call it capital GU. Right. So now, if I want to differentiate this thing with respect to u, right? So the first derivative of this function with respect to u will give you directly g evaluated at this value, right? So that is the fundamental theorem uh, uh, that we are going to use here. Of course, we are going to do this differentiation twice in this case. So let us consider, first of all, let us fix this value. Now, what we have here is fxx and fyv minus x. Of course, it is a function of two mathematical variables, v and u. But let us first fix the v value and consider it as a function of x only, simple x, and let's call it gx. So in that case, I can write down this joint density function of u and joint CDF of u and v I have here as this expression here, right? From zero, negative infinity to u, g of x in that case, right? G of x dx, right? So if I differentiate now with respect to u first, according to the fundamental theorem of calculus, I will get g at u, g evaluated at u, right? So that is this function. But what is g evaluated at u? That will be obtained by replacing x in this expression by u. So that will be fxu and then the cumulative distribution function at v minus u. Right. Now we will consider this as a function of v by keeping u fixed. Right. So I have to integrate I have to differentiate the integration again. So in that case, you will see that when you integrate, you will get this expression. So I have not written down it with the integration and so on. So I invite you to look at it again. But in this case, we are keeping u as fixed and v as the mathematical variable of the function. Right. So thereby we can obtain on the left hand side when you differentiate the joint CDF twice with respect to u and v, we get the joint density function of u and v. The right hand side, as we expected, now we are able to write down this thing in terms of the marginals. marginal density of X and marginal density of Y. Right. So you can write down FUV is equal to this thing, or you can replace this U and V again in terms of X and Y to get this expression here. Right. Okay, so that was a general expression, but let us look at a particular application of that result. Let's look at a particular application, right? Suppose an item is manufactured and then transported to a customer. Let capital X be the manufacturing time of the item. Let Y be the transportation time after manufacturing. Then X plus Y will be the total time, right? Uh, for some products, starting from the starting of manufacturing to until it comes to the uh, customer, right? So suppose we want to find out the joint distribution of X and that quantity, the total time, right? Now we are going to consider particular distribution. In the previous result, we were just considering some theoretical aspects, but here let's apply it uh, with some more concrete distributions. So let us assume that X and Y are independent, continuous random variables where X has an exponential distribution with rate 2 and Y also exponential with rate, say 3, right? Then let's say T is equal to X plus Y. That is the total time from beginning of manufacturing to the delivery to the customer. Right. So if I apply the previous result, we are interested in finding the joint density function of X and T. And then we will, of course, use that to find out a probability also. Let's find out the probability that the manufacturing time is less than 1 unit and the total time is less than 2 units. Right. So if I now use the given information, I can get the individual density functions of X and Y. So fxx will be this exponential density function. Fyy will be this exponential density function, right? X and Y are independent. So using the result, we can say that the joint density function of X and X plus Y, or we can replace this by capital T if you want, evaluated that some X and T has to be equal to this expression from the previous result, right? Product of the marginal density of X evaluated at simple X and marginal density of Y evaluated at T minus X. Right. So we can easily get an expression because we know the individual marginal densities. Therefore, we can get the expression clearly. So this is the expression that we get. The joint density of X and T will be given by this expression, where of course we know that X is between 0 and infinity. T is also between 0 and infinity, but T is X plus Y. Therefore, X has to be less than T. Right. So therefore, more completely, I can write down the joint density function of X and T as this expression, right? Writing down the support uh, explicitly like this, right? So then using this joint density, I will now get this, calculate this probability X less than 1 and T less than 2, right? So for that, again, I recommend you to look at the support and the new subset on which we want to find out the probability, right? So here, this triangle, actually, the whole triangle up to infinity, going up to infinity here, and going up to infinity. X value is going up to infinity. T value is going up to infinity. It's a well, it has a triangle shape. So that is the support where the joint density is positive. But what we are interested in is X less than 1. So X axis is this is the T axis. 1 is here. So x less than 1 is this area here, and t less than 2, right? So t is equal to 2 here. So this is the subset that we are looking at. We want the probability that xy random point, capital X, capital Y random point will be in this gray area, right? So therefore, I have to integrate the joint. So as usual, that what we do, we can look at a vertical stripe, right? First integrate with respect to t over that vertical stripe, right? And then change x from here to here to cover the whole uh, subset, right? So thereby we will get the volume under the joint density over this subset, right? So we will be now, this is uh, x plus y is equal to 2 line. That means y is equal to 2, well, no, this is actually x plus y is equal to 2 line is this one, t is equal to 2. Now this is actually x equal to y line, because not y actually, in this case t, x equal to t line, x equal to t line, because t has to be less than sorry, x has to be less than t. So that's where this region comes from, right? X less than t, right? So this line is t is equal to x line, right? So therefore, when you are integrating with respect to t over this region, t will be changing for a given x. T will be changing from x to 2, right? So that's where this integration comes. This is the joint density. We are integrating with respect to t first, right? So if you consider a vertical line here, the value of t, right? You are considering a particular x for a fixed x, right? So let me just draw it to be more clear. Right. Remember, what we want is to integrate first over this line here. Okay, I'm considering. Right. So this is x here. Right. So we want to integrate with respect to t. So we have to put the limits of t. So t is equal to x here, and t is equal to here. So that's why we are integrating from x to 2 first, and then putting changing x from 0 to 1, right? So we want to cover all these things. So therefore, x will be changing from 0 to 1. So that's why, how we get this probability. So when I do that, I get this answer here, which I can okay, no, what I have here is actually only, first of all, I have calculated on this part, right? This part separately I have got. So I have this expression, and then I have to integrate that from 0 to 1 to get the final answer. And that is equal to 0.8561, right? So you can see that even though the full support is going up to infinity here with respect to t and x, most of the probability is actually concentrated around this corner here. So that's why the probability of the random variable xy uh, that is in this particular subset is very high here, like 0.85. Right. So practically what we can say is that the probability that the product will be uh, produced in less than 1 unit of time, and it will reach the customer in less than 2 units of time, is actually very high in this case. Right. Okay, I think we will look at this example in the next part, because this takes some time. Um, This is also a good example, interesting example, but we will look at this example in part 2 of this lecture.